Hello, everyone. I'm on business trip, so I have pre-recorded the classes for you guys. So for this time, we're gonna start on the me. We're gonna start it on the channel modeling. So for this time, the it's gonna deal with several topics related to mobile and wireless propagation channels using a simulation approach. So that means we will be generating synthetic and realistic series relevant to the propagation parameters uh, as a function of, as we all know, the time and also the propagation distance. So uh, actually, there should be a number of propagation mechanics that, as we all know, all right? Uh, Propagation mechanics. Commonly known as the flexion, diffraction, transmission, and so on. All right. So all these effects are normally caused by the environmental features. All right, close into the user terminal or the mobile station. So furthermore, in some cases, there should be also some larger environmental elements, such as the mountains or buildings that will also intervene in the link characteristics and causing a significant time spreading. Time spreading. So the wireless channel in the with that as the various wired channels that it should provide a distortion-free link between the transmitter and the receiver, all right? So for a wireless link, it should provide a distortion-free link between the transmitter and the receiver, all right? So this is achieved if the magnitude of its frequency response is flat and the phase is linear. So can be achieved if magnitude of its frequency response is flat and the phase is linear. So mathematically, what we can do is, if we assume that the frequency response can usually be represented as the capital H with respect to frequency f, all right? So this is a frequency response. So if the frequency response is flat, that means we can represent it as HF equals constant. And the phase is linear. That means the phase part, right? The phase of HF is linear. That means it's linear with respect to frequency. So F times a parameter alpha. So alpha means it can be a constant, or it can also means proportional to. So this is in the because we represent it as the h with respect to f, so that means it is in the which domain? Should be frequency domain, all right? Sorry. It'll be in the frequency domain. And also, if we wanted to transfer it to the time domain, what we can do is it can be represented as, in time domain, we use this smaller case h with respect to time, all right? So it can be expressed as the what? The amplitude A, exponential part, the J psi times the phase part minus J. I say that it will wrong out of that. And in time domain, so it is an impulse response. So there is a delta function, all right? So psi as the phase. Component. And so that means there is can be a Fourier transform between these both, all right? Fourier transform between these both. So that means the impulse response in time domain can be expressed as HF times equals A, right? And exponential part. And the Fourier transform of the delta function can be this, all right? So this is the Fourier transform between these both. So according to this function, so we can see that a distortion Fourier channel is fulfilled. So actually, the signals transmitted through the radio channel, it usually just employ a limited portion of the spectrum. what it means. So that means the signal transmitted through the radio channel or by the radio channel, it usually used a limited portion of the spectrum. So which is small in comparison with the central frequency of the carrier. The central frequency of the carrier. So such kind of signals are called passband signals. So it is called, it has a name, it's called passband, not band pass, okay? Just passband signals. So for such kind of signal, this is this passband signal and also as the signal transmitted, okay? Transmitted through the radio channel. So it can be expressed as y with respect to time. It can be expressed as the amplitude part times c. Oh. So look at this one. So this is the signal transmitted in the links. So here, AT, it varies with respect to time, all right? So it is the envelope. Of the transmitted signal YT. And the theta T, it is the phase of this signal. So that means for the transmitted information or the signal, transmitted signal, we can call it also modulated, all right? Light signal is contained in the envelope and also in the phase. So all these things, the information is contained in the envelope and in the phase. So that means the signal can be analyzed by just using both terms, right? So what means is there is another parameter is called complex envelope. Complex envelope. Or we can call it also can be called low as equivalent. Of YT. So it can be represented as, use another parameter RT, can be expressed as just the AT, and also because it's complex envelope, so J theta T, all right? So the same thing here, because the signal, so we just take the real part. is a real signal, so we transferred it to the cosine function. But here we use the exponential part, so it can be expressed by this equation and a function, and it will always be possible to recover the yt, the transmitted signal, by from the complex envelope. And how we can do that? I think most of you maybe understand or knows how to operate for that, right? So that means the yt can be expressed from the complex envelope RT by a multiplication of the carrier phasor, and then taking the real part, all right? Because the signal, the transmitted signal, should be a real signal, a real value. So this is how to transfer the real signal or the transmitted signal from the complex envelope by such an equation or such a calculation of conduction. And so also, if we wanted to get the in the complex the real signal by using the RT here and in the frequency domain, so this is YF, all right? So it can be expressed like half that. In time domain, we usually use the uppercase, okay? And in frequency domain, we use uppercase, and in time domain, we use the smaller case. So F minus FC plus the and the complex conjugate of H minus. So what it means? It means the complex envelope can usually be regarded as a version of the passband signal shifted to a central frequency equal to 0 Hertz. So then the spectrum of the passband signal can be put in terms of the complex envelope spectra and then conducted that. And so this is the expressions for the complex envelope. And also, as we all know that the for signal analysis, the complex envelope can usually be put in terms of the two terms, all right? First term is in-phase term. The second term is quadrature components. Two components, in-phase components, quadrature components, and we already expressed the in-phase component as IT, all right? And the quadrature component we use QT, all right, for the presentations. So that means the complex envelope RT, and it can be expressed as T E theta T, can also be expressed as IT, and the imaginary part QT, all right, like this one. So if we want to get the we get the complex envelope of the transmitted signal. And what we're gonna do now? Now we're gonna compute the instantaneous power so instantaneous power expressed as magnitude of the complex envelope absolute of it, all right, square divided by 2 times 2 times R, right? So R is the resistance of the load. And also, this is how to conduct or obtain the instantaneous of the power, the instantaneous power, how to calculate that. Okay, then if we want to get the average the power for a modulated continuous wave. Continuous wave. So that's what we usually do. For the average power, what we usually can do. The first thing is we get the RMS value, all right? The RMS value of the unmodulated continuous wave square. It can be expressed as T, right? That can be expressed like this one, all right? When it is transferred to the complex envelope, all right. But here, there's one thing we need to conduct is because it is for the RT, the complex envelope, which corresponds to a modulated signal. So there should be a half of that. Normally, and it can be expressed as half of the R square R and S. This is important expressions for that one, and because the modulator of KCW wave. So that means sometimes if you want to take the measurements on the modulated signal or the unmodulated signal, you need to take care of the maximum power input to your power meter, and to avoid the it can be destroyed actually. So now the average power can be expressed as divided by the resistance of the load, right? This is y squared r s. And then finally it can be expressed as half here, like this one. And so this is how to calculate the average the power of the unmodulated continuous wave. So unfortunately, the channel response does not remain constant in time as the terminal moves. So that means if for mobile wireless channels, the terminal is always moving, so we cannot making the channel response to be a constant. All right. So then, even though if the terminal is stationary, the time variations may also arise. So if you take measurements with respect to time, you're like, even though your transmitter and your receiver are fixed at the same position and there is no movement on them and there's no adjustment on them, your detected power is usually changing with respect to time. So that's because there should also be some distortion of frequency shifts that are introduced. And there should be also some other effects that's going to be introduced later. So the for this course, what we're gonna more concentrated on are the for example the power. Firstly, variation in power, definitely right, and voltage, and also the phase. All right, to represent the channel, and also the attenuation, power attenuation, or voltage attenuation, and also phase related to the frequency response. For these things. So this is gonna be used to characterize the channels that we wanted to analyze or introduce. So for a wireless propagation physics, what we would like to discuss is there are some effects that should be analyzed or introduced. The first one is the path loss. As we all know, all right? And also shadowing. Another one is multipath. Effect. So this is really depending on the on the location and the base station or the access point height. So for it's depending on the scenarios that we analyzed. So for example, if the cells of a larger or smaller size can be created, the classical cellular environment of tall moss above rooftops this gives rise to a cellular environment is called a macro cells. And if the base station antenna height becomes smaller and is below the surrounding roofs, antenna smaller and below rooftops, we can call that as the microcells. And also, if the base station is within buildings, we call it picocells, much smaller, right? And also there is the last size is when the satellites are used. And there should be a much higher antenna height, all right? We can call it megacells. So that means according to such different kinds of the cell size, the propagation mechanisms should be different, all right? Which kind, some kinds should be dominated, and it should dominate, and some other effects should be much more weaker. So this is all these things. So for an example, such as the buildings or small houses in the suburban areas, with sizes ranging from maybe a few meters to tens of meters, and then the wireless propagation channel should be dominated by, for example, the multipath effects should be considered always. And if in the urban areas, the size of structures can be much larger, and also there should be some other effects that should be analyzed due to the, for example, the blockage and the scattering of the channel signals caused by the, for example, the specular or the diffuse reflections, and so these things. So the we can also classify or identify 3 levels in the range of change of the received signal. Levels of the received signal with respect to a function or as a function of distance. The distance is between base station and the mobile station. So there are 3 kinds. The first kind is called a very slow variation. With respect to the distance or the range. And a second term, that means it is very slow. That means sometimes, for example, the free space path loss, right? So it varies. slow with respect to frequency, and also the second size, the second kind is slow or long-term variation. This is usually due to the shadowing. This is due to path loss. And the third kind is fast, right? Or short-term variation. This is usually due to what? According to here, all right? Due to the multipath components. So according to the multipath components, there should be two representative and extreme scenarios. Representative and extreme scenarios. The first type is called line of sight. We can use the abbreviation LOS, right? And the second time is the second scenario is non-line of sight. Yeah. All right. So for the line of sight, that means there is a strong direct signal and also together with a number of weaker multipath echoes. And for the oppositely for the non-line of sight part, that means there is a number of weak multipath echoes and no direct signal. For this time, the multipath echoes is weak also, but because there's no direct signals, so we can regard it as the non-line of sight channel. And so later we're gonna express it mathematically and why the multipath echoes is always weaker than the direct signals. So there are several cases how to characterize the received signal level due to the reflections, for an example, or due to the line of sight and non-line of sight. So firstly, let's see the picture now. So here is a picture, all right? Now, this picture occurs, this case occurs in an open area or in a very specific spots in city centers. For example, in places like crossroads or large squares with good visibility of base stations. Sometimes, so this is a direct line of sight, can be regarded as that, and so there could also be, it can be a line of sight condition. Oh, sorry. It can also be a non-line of sight, but with a strong specular reflection. So we can see the signal varies of the reflection by a smooth surface. So we can say its received signal level varies with respect to time, like this one, okay? There's also some kind of fluctuations, and so this kind of signal can be modeled by a Rice distribution. For the variation now. So we could call such kind of cases Rice case. So, however, if the signal suffers blockage and also the diffuse scattering, so then that means there should be lots of multipath components, all right? So, and this kind of the received signal, wait a second, please. The received signal can be represented by this one. So then that means it varies like this one. You can see its fluctuations is much more fierce and serious, all right? So this kind of the signal amplitude variation can be modeled by, we can see here, by the Rayleigh distribution. And also we call it as a Rayleigh case. This is a Rice case. So this is due to multipath components. Effect. So here, what we did is we express the received field strength or the received voltage in the time domain. So it can be expressed as the complex envelope with respect to time, all right? So respect to time. We can also express it as with respect to the distance domain. So how we can do that? So now we can say it here. So let's choose a plot on that. This plot. So from this plot, we can see that if there is a base station here and the mobile station this is base station. The mobile station moves, you can see moves along this line and to here, okay? And the received power of the field strength varies with respect to distance, okay? So now if, for example, for a if the mobile station moves with a constant velocity, then it is convenient to relate the complex envelope RT and Rx, all right, because we can get that the distance x equals velocity times time, all right? So we can relate both together by this relationship. And but if it moves, for example, not with a constant speed, and it looks like this plot, we can see that there is this is the overall signal variation, and also we can see there the received signal variation can be broken into two components, all right? The first component is, for example, the dashed line. We call it a slow or long-term variation. And we can name it as MT or MX. The second term is the fast, all right? Or short term. Variation, call it, name it R node E or R node X. So if we want to get the a real complex envelope RT and Rx, so what we should do is we get the product of these two terms. That means this equals MT, product of MT and R node T. And also this term is the product of MX and R node X together. The slow variation and the fast variation together, or the long-term variation and the short-term variation together, like this one. So this is usually a very common expressions for this term. And so sometimes, for example, if we have a signal like, for example, so we have a signal looks like this, for an example. And what we should do is we obtain the slow variations, right? The slow variations like this line, for example. So this is the slow variation. And also together with the first variation, right, we can extract the first variation by removing the slow variations we are right. So what we can do, how to remove the slow variations. We can use a filter to extract that, right? So by using this this approach, we just making the first variations to be superposed on the slow variation. We can get an actual signal here. So the how to get, for example, how to extract the the first variations or the slow variations. So, for example, the slow variations can be extracted from the overall variations through a low-pass filtering, all right? So if we want to get the slow variations, we set a low-pass variations and then filter out all the first variation components of V, and then this can be done, all right? So this is that one. And the slow variations of the signal can also be modeled by this kind of distribution. So previously, we said that certain kind is called the Rice case, and the Rayleigh case can be described by the Rice distribution and described by the Rayleigh distribution, right? So for the slow variations of the received signal, it can be modeled, or it usually follows a log normal distribution. Is if the variation is in the slow variation is in a linear unit. However, if it is in a logarithmic unit, then it is just a normal distribution. This is the characterizations for such kind of signals. And also, the fast variations can be described by the Rayleigh distribution, because there's multiple components right along this range. There should be multiple components exist. Let me check what's the time. Okay, now let's take a short break, maybe, and then we're gonna come back in 5 minutes. Okay, let's come and start again. So as we previously said that the slow variations is usually caused by the path loss, all right? So how to calculate the path loss? The most important is the free space path loss, right? So low variation, example, the free space path loss, free space path loss. So here, if in a linear unit, the logarithmic unit. So for a linear unit, you can get the path loss, really. For a linear side, for example, we expressed as the transmitted power divided by the received power equals 4 pi d over lambda square, as we previously demonstrated, right? So in the logarithmic unit, we use the uppercase, okay? And it can be expressed as, for example, 32.4 plus 20 times log 10 frequency in megahertz plus the 20 times log 10 d in kilometers, right? These two equations are most commonly used. From here, we assumed that we do not consider the gain from the antennas because we assumed isotropic antennas, all right? Isotropic antenna, that means there is a 0 dB or there is to be I the antenna gain in linear in logarithmic units. And from here, we can see that for the free space path loss, distance in kilometer, and the received power relative to the 1 kilometer, okay? So this unit is dB, not dBm or dBw. And so this is 0 example, and so the 1, okay? 10, 20, 30, 40, for example. And it varies usually decays like this one, right? It decays in the receipt following an inverse power law of exponent n equals 2. Am I correct? The relationship between PR and D square. All right, accordingly to this one, such a kind of equation. And so that means it is fixed, all right? But actually, in according to the experimentations, for typical mobile propagation paths, the signal's distance decay does not follow such kind of law. And actually, it varies, decays much deeper, like this, with n equals 4 actual experimental. And which follows a rule like L of D. power n. So L is proportional to the distance raised to the power n, and the value n is around n equals 4, for example. So according to this law, if, for example, in the ITU models or the ITU theoretical models for the power loss distributions, it can be expressed as A plus B times D in kilometers, and must be expressed as A plus 10 times N. Let's make it kilometer like this one. And A and N are dependent on the frequency and also number factors. So A and B, they really get a table about A and the capital N and the parameter N in a table. They, with respect to frequency, it varies with respect to frequency here. And also there are some other parameters that should be considered. The first parameter is height of mobile station. Second is height of base station, right? So the height determines if the base station or the mobile station is very high and there's no blockades and also no multiple other components, then the values for A and N should also be changed, all right? And the third parameter is the terrain irregularity. For example, the roughness or the undulation as we previously demonstrated, all right? And the fourth one is the land usage in the surrounding of the mobile station. For example, the urban and the suburban, rural, open area, going to be different. If you read the ITU report, you're going to find all these things. And so then the path loss can be calculated based on the error, the reference, right? We calculated and we used and times the terrain irregularity. And the time plus the path loss due to the environment. So if we wanted to calculate or conduct the link budget, as we previously demonstrated, all right, it can be expressed as the received power. For an example, dB expressed as the transmitted power. The capital case it represents the logarithmic unit plus the gain of the transmitter side plus the gain on the receiver side minus the transmission losses at the transmitter side, the loss at the receiver side, and the loss in the path due to the path. Okay, and and the liberties are already computed in terms of the received power, but also in some cases it can be related to the, for example, the power flux density. By and also the effect and also the effective antenna aperture AE. All right, so then the received power can be expressed as phi times AE. All right, and AE is related to the antenna gain. All right, AE can be related to antenna gain. For example, 4 pi times AE divided by lambda square equals the gain at the receiver side in linear range. All right, and the power flux can be expressed as half of that A square divided by eta, and eta is the impedance. All right, eta equals the impedance, and A is the actual field strength in linear range. So the field strength in linear range, so it can be equals divided by 120 pi. All right. So finally, or actually, as we previously demonstrated, it can be expressed as the in the linear range. All right. So we set it in linear or in linear unit. The received power divided by the transmitted power can be expressed as first things the transmitter side again, the receiver side divided by loss and receiver side, right? So free space loss. And also if there, this is for the line of sight, okay? And for non-line of sight, there should be a part, all right, or a reflection, all right? So for a reflection part, that means there should be a reflection coefficient related, right? Or the reflectivity, for example. So, all right, reflection coefficient divided by 4 pi distance, the first distance and the second distance, all right, before reflection, after reflection, square this one. And finally, it can be related to, for example, at the transmitter side, and 1 over 4 pi d1 square, and times the biostatic radar, all right, for the radar cross section, and times at the receiver side 4 pi d2 square times gr over lr, all right, and there is also another term is related to the square divided. So this is for the biostatic radar equation here. So when we come back to the line of sight, for example, compare that with the line of sight part. So we can see that there is the capital D. The line of sight also for the non-line of sight with the specular reflection. So it can be related to this one also and this one. All right. So they consider a reflection coefficient together with that. And so that means we can see here. So if for a specular reflection, we have the 1 over d1 plus d2 square, right? And for the diffuse scattering, for example, for different kinds, the directions, actually there as d1 square times d2 square, right? So that means from this equation, even though for a much longer distances, so the this term is much smaller than this term, right? So this one gonna be much larger than this one. So that means for even though for the non-line side components or the multipart components, the specular reflection or reflected component should also dominate. Will always dominate. Even though for the radar cross section is a large value. So now, so far, we have discussed the static power link budgets. Link power budgets. So in fact, the received signals are time varying, all right? Am I correct? So the received signal is always time varying. So to account for such variations, when we wanted to compute the system outage probability of setting up a fade margins, the distribution of the variability, such as the fast and slow variations with the received signal, should always be well known. So a good statistical knowledge of the signal variability behavior is of paramount importance for optimal system planning. So that's what we gonna to do next. So, and for the general modeling, I would give you guys homework about the separation of the low variations and the fast variations if there is a signal recorded by a parameter. And I hope you guys can do that by using the MATLAB programming. And I think it is not very hard and should be very easy for you guys, and maybe take you just half an hour or 1 hour, something like that. And then I'm gonna see you guys next week. Okay, bye.